Welcome back. So we are going to discuss the second case. So this is how to find electric field on the equatorial line of electric dipole. So the second case is electric field on the equatorial line of electric dipole. So this is what we are going to discuss. Now for this I will draw a dipole here. So this is the dipole having minus q and the plus q here, and this is the length of the dipole, which is equal to 2a. The length of the dipole is 2a, and this is the center O of the dipole. Okay, now let us consider any point on the equatorial line, and line passing perpendicular to the center of the dipole. Okay, so this is called equatorial line. So let us consider any point P here, any point P which is at a distance r from the center of the dipole. So let us take this point A and let us take this point as B. Now let us see what happens. So the distance from here to here, this is A, and this is also A, and this is your point O, the center of the dipole. Now the distance from here to here is AP, and the distance from here to here is BP. Now let us see what happened here. So this is minus q charge. So the electric field at this point P, due to minus q charge at A, will be, look at this, EA, and the direction will be towards the negative charge. Okay, towards the negative charge. And now if we take the electric field at this point P due to plus q charge at B, and this will be away from the positive charge. We have to mark this as EB. So there are two electric field, EA and the EB, and only what we are going to do is we have to find the resultant of the two electric field, and that resultant will be the electric field due to this dipole. Okay, so we have to find the resultant electric field on the equatorial line, and this is what we are going to find out. Okay, now let me start. Consider an electric dipole of length 2a. Consider an electric dipole of length 2a. Okay, now let P be any point which is at a distance r from the center of the dipole. Let P be any point which is at a distance r. P be any point which is at a distance r from the center of the dipole. Now, then we'll find electric field at P due to minus q charge at A is given by minus q charge at A is given by EA equals to K Q divided by the distance square, which is AP square. So I will write KQ. Then now comes to what is the distance AP square. So AP is the hypotenuse. So I will write AP as R square plus A square according to Pythagoras theorem. So I will write this R square plus A square. Now this is the magnitude of A here. Again, electric field at P due to plus q charge at B is given by EB magnitude equals to K Q by BP square, and this equals to K Q by R square plus A square. Now the one interesting happen here, that means both E and the EB are equal in magnitude, but they are having different direction. So EA along this direction and EB along this direction. And now let's consider this angle as theta. Now let's consider this angle as theta, and this angle also having theta. So now if this angle is theta, then this is theta and this is theta. Okay, now what is the net resultant electric field here? So we have to find the resultant electric field E here. So since magnitude of EA is equal to magnitude of EB. Look at this, magnitudes are equal. Now how to find the resultant of this? Now let us see here in this figure, this is point P, and now you will find from here that this is EB and this is your EA. Now let me consider this point here. So EA can be resolved into two components. One is, this is angle theta here. So EA can be resolved into two components, EA sine theta and EA cos theta. Look at this, EA can be resolved into two components, EA sine theta and EA cos theta. Similarly, EB can also be resolved into two components, EB sine theta and along this EB cos of theta, as this angle is theta. Now at this point P, we resolve EA and the EB into two rectangular components, EA sine theta and EA cos theta, EB sine theta and EB cos theta. But here, since EA and the EB are equal in the magnitude and the value of theta are again equal, so EA sine theta and EB sine theta are equal and opposite, so they cancel out. Okay, since these two cancel out, so the net electric field at this point P will be the sum of EA cos theta and the EB cos theta. So that is why we can write, therefore the electric field on the equatorial line is equal to magnitude of EA cos theta, that is the component, plus EB cos of theta, the two components. So if I put the value here, then this further obtain E equatorial is equal to EA and EB are equal in magnitude, so can I write twice EA cos of theta. And now if I write twice what is EA, it can be written from here, so K Q by R square plus square. And now what is the value of cos theta from this triangle? Cos theta is adjacent side by hypotenuse. So adjacent A and the hypotenuse is R square plus A square power half. So according to Pythagoras theorem and trigonometry, I will write cos theta is A divided by R square plus A square to the power half. So we can write this as here 2Q into A is K, Q into 2A will becomes P dipole moment divided by K हो गया 2QA हो गया R square plus A square power 3 by 2. So this is the required equation for electric field on the equatorial line of the dipole. That means K times P, that is the dipole moment, R square plus A square 3 by 2. So let us see the case here. If A is very less than R, that means For a very short dipole, what we get here, the equation can be written as E equilateral can be written as Kp divided by R power Q, or we can write this as E equatorial is inversely proportional to RQ. So here we get E equatorial is again inversely proportional to R cube. But here what interesting thing happened here is the dipole moment is P here. So the dipole moment is what we get? The dipole moment is again opposite in direction to that of the electric field. Here electric field is opposite in direction to opposite to that of the P. Okay. In the previous case we get electric field in the same direction of that of the dipole moment, but here in this case electric field is in opposite direction to that of the dipole moment. Thank you.